Okay. Record to the pod. Okay, take it away. We're happy today to have Philip from Cincinnati. Please welcome.
Thanks. Yeah, thanks for inviting me. So I'm going to talk about a vertex algebra of extended operators, meaning like line, surface, and so forth operators in four-dimensional n equals 2 superconformal field theories. So this is work that I'm doing with Matteo Lotito and Mitch Weaver. And as you'll see, it's kind of a work in progress. I'll give you a sort of a status report of where we're at. We're going to be writing up more or less the content of this talk, but you'll see that there's quite a bit more that needs to be done. But what I will be able to show you is that for any kind of a universal construction of an extension of the vertex operator algebras that occur for four-dimensional n equals 2 superconformal field theories. So let me give some, a very quick summary of the results, and then we'll go into the details in the rest of the talk. And the story starts, 10 years ago with the paper of Beam, Lemos, Liendo, Piliaros, Rastelli, and Van Rees on the vertex operator algebras. And let me just remind you of what they did, and I'll do a somewhat more detailed review in the talk. But they picked a supercharge of the superconformal algebra, a nilpotent supercharge. I'll call it T here for twisted Schur supercharge. And then they looked at the local operators, which are in T, the cohomology of T. Those are the so-called Schur operators. And they put them on the x1 equals x2 equals 0 plane in space-time. And let me put a complex coordinate on then. So I'll call that the x3, x4 plane that they live on. And I'll put complex coordinates on that plane. So z and z bar. And why this particular plane? Well, it actually has to do with the specific choice of supercharge that you choose here. Obviously, you could rotate it to any plane. And then you look at the correlation functions of these Schur operators. And because they're annihilated by T, they're in the cohomology of T, they satisfy some Ward identities. And in particular, they imply that they do not depend on the anti-holomorphic coordinate on this Z plane. And so they are locally holomorphic in Z. And then together with unitarity, you learn that they're in fact these correlation functions are in fact mirromorphic functions. That is to say, no cuts or worse singularities on the Z plane. So it's looking something like a chiral half of a two-dimensional conformal field theory. And in fact, they're able to find one of these operators, which we'll call T of Z, which has the usual Virasoro, whose modes satisfy the Virasoro algebra. And with respect to that one, you can organize the Schur operators into primaries and descendants given by dz derivatives in the usual way. And so if you have this structure, this kind of chiral, single-valued chiral half of a 2D CFT, that's called a vertex operator algebra. Okay, and now there's all sorts of implications and beautiful things that you can understand. This is turns out to be a very powerful tool, especially for understanding things kind of related to the Higgs branch structure of the conformal field theory. So it's less obvious how to see the Coulomb branch geometry, how that's encoded in this VOA. So, maybe as motivation, one thing you might expect is, well, if I can't see the Coulomb branch, or more specifically the special Kähler you can see kind of the Kähler structure of the Coulomb branch, but you can't see the full special Kähler structure in the Coulomb branch, that the lattice of charges with respect to the unbroken U1 gauge groups on the Coulomb branch. So how might you expect those things to be encoded in terms of gauge invariant conformal field theory data? Well, the obvious gauge invariant operators that you would try to write down in the Coulomb phase would be Wilson-'Natouf line operators. So you might guess that at the conformal vacuum, that maybe we should enhance this whole VOA structure, instead of by looking just at local operators in the conformal field theory, try to extend them to line operators. So this motivated these natural questions. Are there extended line, surface, whatever operators in twisted Schur cohomology? And if so, what are the structure of their correlators? What kind of algebra do they satisfy these? They're no longer point operators. As we said, the VOA came from putting the point operators on a plane. What can you do with the line and surface operators? And so the answers to these questions are, and this is what this talk will try to explain in some detail, is first of all, yes, there are line, surface, wall, even volume filling extended operators in twisted Schur cohomology. And in fact, I'll give a construction, which is basically the close cousin to topological descent construction in topological field theories. For every local operator in the cohomology, I'll generate a whole set of extended operators of various dimension. And so this is a universal construction. And furthermore, we'll see that when you write correlators of these operators, they end up also only depending meromorphically on a position, like you can think of it as where these operators intersect this VOA plane. So they look like they're giving an extension of the vertex operator algebra, adding more vertex operators in the vertex operator algebra. However, these guys can no longer, these extended vertex operators can no longer be organized into primary descendant modules with respect to this the vertex operator algebra and kind of chiral stress 2D stress tensor field. So if you have a vertex algebra but without a good chiral stress tensor field, then that's just called a vertex algebra. And vertex operator algebras, also sometimes called conformal vertex algebras, are vertex algebras which have that additional structure. So what we're finding is the extended operators give an extension of the vertex operator algebra to a larger but maybe less structured object, a vertex algebra. And so here's the outline of the remainder of the talk. One, I'll give a more detailed review of the ingredients of the vertex operator algebra construction that we need to see this, and then use those to introduce this descent construction of the extended operators. And then we'll take the first steps to understanding the actual algebra, the operator product expansion, if you like, the operator algebra that these extended operators and the local operators all satisfy by actually computing in an example, namely a free hypermultiplet. Okay, so I will give you some partial results on what the vertex algebra of this extended vertex algebra of a free hypermultiplet superconformal field theory looks like.
Philip, you have a question in the chat.
Okay. Maybe I should open the chats here so I can see that.
Yeah, I can read it to you. But by the way, if people have questions, you can just unmute yourself and ask.
Yeah. I said, please interrupt me. That's a lot easier than me trying to look in the chat.
Okay, so the question is, would you not expect extended operators to give rise to categories related to the VA or VOA?
Maybe the categories were, related to the VOA.
Yes.
I don't really know the answer to, I don't have a good answer to that. At the moment, I'm taking maybe a slightly more lowbrow approach, which is trying to compute in some examples to get a sense of what's going on. But I certainly don't see a simple sort of, we'll see during the talk and you see how the construction goes, that it doesn't have a really simple relationship, at least it's not apparent to us at the moment, to the vertex operator algebra, that you do some sort of simple thing to the vertex operator algebra and to extend it to this larger vertex algebra. But that's not to say it doesn't exist. Maybe we're just not understanding the kind of what to do algebraically at the level of the vertex operator algebra, the vertex algebra. Other questions? Okay, good. So I'm going to fairly rapidly give a review of the vertex operator algebra story, emphasizing some points that towards the end that might be a little bit you might not be, even if you know the story, you might not have appreciated. And then but slow me down if you have any questions. So first of all, I'm just going to set up a little bit of notation about the four-dimensional n equals 2 superconformal algebra. So first of all, it has, of course, the conformal part and the U2R symmetry part with the usual generators, translations, rotations, dilatations, special conformal transformations, U1R and SU2R. So the AB indices are SU2R indices. And the fermionic part has the supercharges Q left, Q right, Q and Q twiddle, and then the superconformal charges S and S twiddle. And then two involutions, which will be useful for organizing things. One is the adjoint anti-linear involution, which is the adjoint in radial quantization, and so that switches P's and K's and Q's and S's, and then a kind of a chiral involution, a 2 pi chiral rotation, which basically just changes some signs on the Q twiddles and S twiddles, but not on the Q's and S's, and similar to P's and K's. Okay, they'll just be a useful sort of organizational tool. And then here are some coordinates. If we're in Euclidean space, I just call them x1 through x4. Remember, when by going to the cohomology, by picking a specific Schur operator and going to its cohomology, I'm going to be basically breaking all my symmetries. So I just have to set down a coordinate system in order to talk about this sensibly. When I go to Minkowski space, and as we'll see, we're sort of forced to work in Minkowski spacetime, not in Euclidean spacetime, then x1 will be my time direction, and the other one's the spatial directions, and it will be convenient in the x1, x2 plane to introduce x plus, x minus light cone coordinates, whereas in the x3, x4 space-like plane, I'll introduce z and z bar complex coordinates. Okay, so the x plus minus equals 0 plane, that is to say the z bar plane, is that vertex operator algebra plane that we'll be using. But all these other coordinates are going to come into play. So now I have to pick my twisted Schur supercharges. They're not unique. You can if I take any given choice, I can conjugate it by all sorts of things. But let's take the choice that was taken in the original paper. So it's a certain nilpotent linear combination of Q and S twiddle. That kind of isn't covariant with respect to the SU2R symmetry. So these are the Lorentz generators, and these are the indices, and these are the SU2R indices. And then T dagger, T chi, and T dagger chi are three other guys. They're also nilpotent versions of the twisted supercharges. And as we'll see, though, even though we're going to be working in T cohomology, it's going to be important to kind of keep track of what's going on with respect to these other four in this set of four supercharges. They don't form a nilpotent subalgebra by themselves, right? They don't necessarily anti-commute with one another. And so linear combinations of them are not necessarily nilpotent. So these are just four discrete nilpotent fermionic operators. Okay, good. Now let's look at the cohomology of this operator. These are the local operators, which are so-called Schur operators, are the guys in this cohomology. Any operator has its left and right space-time spins, which I'll label by integers instead of half integers, and an SU2R spin, which I'll label by integer R instead of half integers again. And so they just count the number of symmetrized indices, if you like. And a Schur operator is an operator with some arbitrary SU2 and Lorentz indices, such that its dimension is related to R, J, and J twiddle in this way, and its U1R charge is related to J and J twiddle in this way. And furthermore, it's the component in that representation, which is kind of the top component, the highest weight component with respect to all of these three SU2s. So this is a description of the Schur operators. And it's not too hard to see that every kind of every supermultiplet which has a shortening conditions on both a left and a right shortening condition, so every sort of double short or double-sided supermultiplet will have a unique Schur that's a conformal primary, and then an infinite set of its conformal descendants, of descendants which are also Schur, which are just the derivatives with respect to Z of that O. That sometimes the Schur primaries are also the super conformal, they're not just conformal primaries, they're super conformal primaries for certain multiplets, the BB bar multiplets, but for the other multiplets, they're not. And then, as we'll see below, a Schur operator, though I just asked that it's in T cohomology, by unitary, as long as my conformal field theory is unitary, then it's also automatically in the cohomology of these other three nilpotent operators. So, okay, good. So here comes the interesting thing. Of course, we don't have to just, we can ask whether the actual generators of the superconformal algebra itself are in the cohomology of T. That is to say, we can look at the subspace of the superconformal algebra of T closed generators annihilated by T. And then there's a subspace of that space, which are the T exact ones, because T is nilpotent. And in fact, using the Jacobi identities, these are not just subspaces, but actually Z and B are sub-algebras, sub-superalgebras. And B is actually an ideal in Z, so the quotient is also a subalgebra of the superconformal algebra. Okay, so what we have a specific T, we know our superconformal algebra, it's completely straightforward to just compute these. And so let me, and so the closed subalgebra, I can write as, break it up into some pieces in this way. I define an SL what I'll just call SL2, and I'll name its generators L-1, L0, and L+1. And they are the holomorphic translation in the VOA plane, a rotation in the VOA plane plus a dilatation, and the special conformal transformation in the VOA plane. This is kind of like the holomorphic half. And then the SL2 hat is, if you look here, it's more or less the anti-holomorphic half of that thing, but plus the diagonal subgroup with the SU2R generators. So in the language of the original paper, this is an SU2R twisted sort of anti-holomorphic SL2. There's also a U1 generated by the U1R charge, U1Z generated by the U1R charge plus boosts in the transverse 1-2 plane. And then two other nilpotent algebras, M plus and M minus, which are given by these generators. And it's going to be crucial to see that these light cone translation operators are in M plus or in M minus. Okay. So now here, these are just definitions, but I took a little time with them because they're going to play a central role. Then the T-closed operators in the algebra are given by these guys, the SL2 plus SL2 hat plus the UNZ plus the M plus guys. And all the guys in blue are actually exact. So the cohomology is just Z mod B is just the SL2 subalgebra. You can do the same thing for the T dagger chi cohomology, which will turn out to be important as for reasons that we'll describe. And it's almost the same, but instead of M plus, it has M minus in its cohomology. Okay, good. So what do we do with these cohomologies? And ignore this. You don't have to worry about the fermionic generators, and there's some other stuff here that let's skip over that for the moment. So these algebra subalgebras of closed or exact operators are important for the following reason. If I have an operator at the origin that's in T cohomology, and I translate it by any group element generated by an element that's T closed, right? Remember, these are some space-time symmetry generators, so that they typically will move this this operator away from the origin to some other point in space-time, depending on X and alpha, and maybe also do some rotation of internal indices or the Cartan indices. But whatever it does, because this is closed, it's easy to check that if O is in T cohomology, then this whole thing is also T closed. So way of thinking about the closed subalgebra is that it's the one that generates configurations of T closed operators starting from a given T closed operator. So it moves you around on the configuration space of these T closed operators. And the subalgebra of this, made up of the exact generators, well, so what do they generate? Well, in T cohomology, because now we're saying that the generator is exact, then it's easy to see that this translated operator in T cohomology differs from the original operator that we had, let's say, at the origin by a T exact piece. So they're equivalent in cohomology. And so by the usual word identities, correlation functions won't depend on this parameter. So you can think of the exact subalgebra as generating symmetries, if you like, motions on this configuration space under which the correlators of T closed operators are invariant. So let's see how this works out. Let's let's look at for the closed operators in those algebras that I had above and ask which one, if I put an operator at the origin, which one of those operators will actually move the operator. There's a lot that are in the isotropy group of that point. I'm going to go back up here, and here's our subalgebras. I get to look at all of these operators. They're all T closed, but the rotations, dilatations, R symmetry transformations, and special conformal transformations, all of these guys do not move the origin. The only ones that move the origin are the translations. So the only operators that we're interested in are L minus 1, L hat minus 1, and P plus if we're doing T cohomology, P minus if we were doing T dagger chi cohomology. So the only operator, the only motions that I can do to make new T closed operators starting from the ones at the origin is it would be some sort of group element of this form, this 3-parameter family. And to keep it a real motion, I need Z and Z bar to be complex conjugates, right? So these things will just generate, in addition to a rotation of the internal SU2R indices, they will generate a translation in that Z plane. And this one will also generate a translation perpendicular to the Z plane along the X plus light cone direction in the 1, 2 plane. So this part here might be a little unfamiliar, but we don't actually have to put our Schur operators actually on the x1 equals x2 equals 0 plane in space-time. We can actually put them anywhere we like, but we just see that they only, the correlators only depend on the Z coordinate. And so if it's some, you can always equivalently put the correlators back, you know, say they're equivalent in cohomology to setting this X plus coordinate to 0. So following that light ray back to where it intersects the VOA plane. Of course, this only worked in Minkowski space because the P plus generator is only generates a real translation in Minkowski space. In Euclidean space, this would be a complex transformation, so it would not give rise to another local operator in Euclidean space. Okay, so this was how you recover the Ward identities, that, you know, the fact that the correlators only depend on this holomorphic, this complex coordinate holomorphically on the Z coordinate on this Z plane. Okay, and that's locally holomorphically. They may have cuts and so forth. You might worry, but it turns out, again, following from unitarity essentially and superconformal invariance, that the spectrum of the L0 operator is always a half integer, and that turns out to be enough to imply that you have no cuts in the in these correlators on the Z plane. So they're just meromorphic functions of Z. Okay. Now, it also turns out, following from representation theory of unitary conformal operaters, that well, from the being in the cohomology tells you that the O's are in the kernel of L naught hat, but they're also, unitarity tells you they're also in the kernel of this other Z operator. And using that algebra, that immediately then implies that if an operator was in T cohomology, then it's actually automatically in T dagger, T chi, and T dagger chi cohomology. Okay, good. So that's my lightning review of the kind of the algebraic underpinnings of the whole vertex operator algebra story. So now maybe I should pause there if there are any questions. What I'm going to go on to do now is then remind you of the so-called topological descent construction of extended operators in cohomology, and then apply it in this case, in a more or less straightforward manner, as you'll see. Well, there's some, we'll see that some interesting things happen which have no analog in the topological field theory setting that topological descent was first put in.
There's a question, David, go ahead.
I'm just going to quibble about your use of the symbol for rational numbers for a supercharge.
I don't use this. I actually changed my supercharge to T here so that I wasn't using Q.
I see.
So I should. So, but you should take it up with Beam and company, since they use double struct Q for their supercharge.
Next time I see Chris, I will bring it up.
Don't they use square double struck?
Yeah, they did use, you're right. They did use the square double struct, but I can't, that's too much trouble to write by hand. Anyway, so yes, I am going to use double struct Q for the nilpotent supercharge in that was used by Witten in his original topological twist paper on topologically twisting 4D n equals 2 super Poincare supersymmetric theories, but without necessarily having super conformal invariance. So he picks a certain nilpotent supercharge, and again looks at local operators in their cohomology. And now this supercharge is such that all the translation generators are Q exact. And in particular, that means I can write them as Q acting on some other fermionic generator, which I'll just call Q sub mu. It's the fermionic generator related in this way to P mu. It's not unique, but it differs by exact pieces. So then that tells me if I translate any operator in Q cohomology, and the operators in Q cohomology in this case are these Coulomb branch operators. If I translate them, they are in cohomology equivalent to the operator at the origin. That is to say, that these are completely topological operators. Their correlation functions won't depend on their position unless they happen to coincide with the position of another operator. So this is the very simple analog of the VOA story, except here it's just completely topological for these in this case. Now, it turns out, and it's kind of obvious in the super Poincare algebra, that these fermionic operators actually form a nilpotent subalgebra. So they're nilpotent Q mu squared, but also they anti-commute with Q nu for nu not equal to mu. And that from this, it also follows that they commute with all the P's. And these conditions allow us to make this beautiful construction of non-trivial cohomology classes associated to arbitrary closed n cycles in space-time. So I'll call that operator based on a given local operator in Q cohomology. I'll call it sigma sub n of O, and it's simply given by this following construction. It's an integral of a closed n form over sigma n, where the closed n form is the following thing. I take my local operator and I act on it with n of these Q mu's, okay? Because they anti-commute with one another, this is anti-symmetric, so I can make an n form, naturally, an n form out of it, and then I can integrate it over any n cycle, or n chain, in fact, to define some operator. So you now immediately see, using this algebra, that if you take if you act with Q on this operator, when it will annihilate the O, but if it hits one of the Q's, the Q mu's here, it will give a P mu, so it gives a total derivative. So if sigma n is an n cycle, then this is closed. And so I've defined in this way a closed n extended operator. And furthermore, in Q cohomology, it's easy to check again using these properties that this n form is a closed n form. So this is again, these then again define topological surface operators. They only depend on the homology class of sigma n. Okay. Okay, that's just reminding you of topological descent. And the point is that, well, getting topological operators in this way, that depended on the details of this particular Q and the super Poincaré algebra. But I can certainly apply this just to this strategy to construct extended operators in the cohomology of any nilpotent operator. So all I need to do is, for any closed generator, find its associated, let's say it's bosonic closed generator, find its associated fermionic Q mu. That's some fermionic supercharge. And then I integrate the original local operator translated by that exact generator, but the super descendant of that operator. So acted on by those Q mu's, right? And that will generate and integrate over that. And so that will, for each time I do that, I will add an extra dimension to the world volume of my extended operators. Okay. So let's just, I said that in words, maybe that wasn't too clear, but let me just apply this. So what I need to look for, I have to ask, what are my T exact generators? I've rewritten them here for you. I've got an operator at the origin, and then I want to find a T exact generator which will move the origin, and then I can integrate over it. So I just have to look which of these generators move the origin. Well, L-1 and P+ do. It's the same thing that we said before. These are the only exact ones, but L-1, if I exponentiate it, does not give a real transformation. So I'm not be integrating, I will not be constructing in this way a line operator in space-time. But P+ does, at least if we're in Minkowski space-time. So I can use this descent construction to construct a line operator by translating my guys along this exact light cone direction, this T exact light cone direction. So P+ is, we said, is exact. That means it's T of something, you know, explicitly with my choice of T and so forth. This is what it is. So I'm just copying the descent construction. I define a line operator associated to a given local operator, Schur operator O, by translating that local operator along that particular light cone direction. That is to say, I started at the origin and I keep all the coordinates invariant, except I just shift it along the x+ coordinate. So this is not like a topological line anymore. I just have this one exact operator that I can use. So I get a straight light ray. And I integrate it along the light ray, but I'm not integrating my Schur operator. I'm integrating a super descendant of my Schur operator. And then just by the above construction, it's going to automatically be in T cohomology up to boundary terms, up to a total, it's T variation. The action of T on it will be a total derivative. And so you have to worry about convergence issues at infinity, but it's easy to see, as long as this thing has positive conformal dimension, that it does converge at infinity. So in correlators. So indeed, this is a nice, well-behaved T-closed line operator. Okay. I said I'm calling it a line operator at 0 because it's going through the origin of the VOA plane. So just to make a little picture of this, here I'm trying to draw space-time in terms of time, that's x1, x2, and those are transverse to the VOA plane, the Z plane, which are the x3, x4 directions. So I'm just writing one of those guys in green, supposedly sort of sticking out of the page. And then for this L plus descent line, if the original operator is at the origin, then its descent line is this light line in this particular direction, perpendicular to the VOA plane and intersecting the VOA plane at Z equals 0. The other thing to note, that if say O is bosonic, remember P is bosonic, T is fermionic, so Q twiddle is fermionic. So this is a fermionic light operator, or at least it has opposite statistics to the Shor operator. So of course, yeah. And these sorts of light ray, local operators integrated along light rays have been discussed quite a bit. They were introduced by Kravchuk and Simmons-Duffins, 4 or so years ago. And so these are a lot of the things that they say about their light ray transform operators also applies here, though ours are not. This construction turns out not to be a special case of a light ray transform. The light ray transform picked the polarization, the Lorentz indices of the operator that you integrate, and chose its polarizations to be, in some sense, parallel to the light ray direction that you're integrating, and that's not the case for this particular set of operators. Okay, so again, I'm pausing just for questions. Hopefully, this seems pretty straightforward. If you've gotten the whole descent procedure, I can do exactly the same thing with respect to T dagger chi cohomology instead of T cohomology. Since O is in both of them, I can make a line operator in T dagger chi cohomology, because in T dagger chi cohomology we have P minus instead of P plus in the exact pieces. So I get a light line operator automatically in T dagger chi cohomology, which it goes on the opposite light ray in the x1, x2 plane. Okay, and I'll call those the L minus transforms of O. Okay, but so far L plus is in T cohomology and L minus is in T dagger chi cohomology. And even though O is in both of those cohomologies, it's not obvious. There's no a priori reason why these two should be in both. And that's the magic, that there is some algebra that these operators satisfy. Remember, let me maybe go back up here. So the whole point was, for instance, the Q minus was defined such that T dagger chi on Q minus was P minus. But it turns out that Q minus is annihilated by T. That's just something you have to check in the algebra. And furthermore, T on P minus, remember P minus was not closed with respect to T. It was closed with respect to T dagger chi. but T acting on P minus closes on minus Q minus, and similarly for the Q twiddle pluses. So this is, I don't know, kind of any quick argument to see this other than actually kind of computing in the superconformal algebra. But these relations then imply, by just a few lines of algebra, which I'm not showing you, but then you just look at this guy, L minus, which we said was in T dagger chi cohomology by virtue of this relation, which just told you that T dagger chi acting on it gave a total derivative. But now you act with T on this, and you use this descent subalgebra relations, and then you show that L minus is annihilated by T. And so, somewhat unexpectedly, L plus is not only in T cohomology, it's also in T dagger chi cohomology, and L minus, so forth. And in fact, now using some other properties of unitarity, or if you like, the kind of representation theory of the Schur operators, you also learn that they're also in the cohomology of the other guys. So they behave a lot just like Schur operators, that you only ask for them to be in the T cohomology, but then they turn out to be in the cohomology of all four of these operators. And what makes this interesting is now we get to continue the descent procedure, because now I can look at this L minus line and I say, oh, I've realized it's in T, it's actually in T cohomology. So now I can try to do T descent on that. But remember, an exact generator that I have in T cohomology was my P plus generator, but P plus moves the L minus line. It actually translates it in the whole X1, X2, or X plus X minus plane. And so by doing descent with respect to P plus on L minus, I will sweep out a surface operator whose world sheet will be the whole X1, X2 plane, or X plus X minus plane. Okay, so here, so this is just plugging it into the whole descent procedure, and so I can do a P plus descent of L minus. So I take my L minus line and integrate it over L. It translates over L plus, but I have to hit it with another supercharge. Or I can do the opposite order, but it's easy to see that they're actually they're equivalent. So it doesn't matter whether I do P plus descent of L minus or P minus descent of L plus, I get the same operator, which we'll call S of O. So here's the picture now. For every operator, let's say at the origin of the Z plane, in this transverse X1, X2 plane, I have an L plus fermionic line, an L minus fermionic line, and an S bosonic surface operator, transverse to the VOA plane, all intersecting the VOA plane at this point.
Are you going to address the boundary contribution?
I'm sorry?
The boundary contribution.
Yeah. So I just stated for you that the boundary contribution is 0 in vanishes in correlators. So that when I say these things are in cohomology, all that really matters for me is if I put them in correlation functions that any terms that I drop are things which are 0 in these correlation functions. So to be strictly, in other words,
is that so obvious for the surface operator?
It's not obvious. To be a little more honest, what's easy to show about all these constructions, that if I have correlators of local Schur operators and these lines or surfaces or whatever, then the contributions from those boundary terms with these operators goes to 0. It's just basically because of the fall off of correlators. between fall off of correlators in a unitary conformal field theory, right? Things where everything has positive scaling dimension. But it's a lot less obvious if I'm looking at correlators of lines with lines or surfaces with surfaces and so forth. So you might worry that now we have contributions from boundary contributions from both, and they may not give zero. So it's a little bit delicate. And let's just say, in the examples that I'll show you in the free hypermultiplet, I will show you the first place that it happens where where some of these integrals of the correlators of these objects, which remember, these objects, these descent lines and surfaces and so forth, they're just integrals of local operators over these world sheets. And so their correlation functions, essentially you can pull the integrals out, and there's some set of complicated integrals of local correlation functions. So you can ask what are the first cases in which you have to worry about getting divergent contributions from these boundary terms. And so I'll point out where that first occurs. Okay. So you might think, well, there's another thing that you can that follows just from the descent algebra is that if the Schur operator has weight h with respect to L naught, which this is like the chiral conformal dimension from the VOA point of view of O, it then follows that, and it's not completely obvious, but it then follows that its descent guys, lines and surfaces, have the same weight h. So that tells us that we're doing some extension of the VOA by these line and surface operators, at least the ones that I showed you so far. But it's not like a super extension. It's not like I have a kind of an n equals 2 super Virasoro algebra coming along here. These fermionic partners of O, I don't increase the dimension by a half or by 1 for this guy here, right? Instead, I keep the dimension the same, and all I'm doing is kind of changing the statistics. So it's more like some kind of ghostly extension of the vertex operator algebra, or its vacuum module at least. So here in summary is this is the picture as I presented it so far. You've got my local operators, and then I can do either P plus or P minus descent to get these light-like line operators, and then do another descent to get this time-like, if you like, surface operator, all perpendicular, transverse to the VOA plane. And I'm labeling it by the point where they intersect the VOA plane. And of course, if I put this operator at the origin, we saw we could translate it, do that so-called twist translate in the VOA plane to any other point in the VOA plane. And for the descent procedure, I can either take the twist translated O and do the descent procedure, or I can take the descent and line operator at the origin and twist translate that. That all works. And those two operations commute. So there's just one. These guys just have unique twist translated versions on the VOA plane. So I can look at their correlation functions by putting them at different points in the VOA plane. They do not, their world volumes, if they're at different values of Z, their world volumes do not intersect, except perhaps in the case when I have multiple surface operators, then they actually end up intersecting at the point at infinity on the VOA plane. And so you have to worry about whether this gives rise to a divergence or not. And then actually, maybe I'll say a comment about that at the end of the talk. You really have to keep track of the fact that these surface operators in the conformal compactification of this whole thing hit the point at infinity in the Z plane as well. And so if you have the OPE of two surface operators, you need to separate them not only at Z, but also you have to separate them at that point at infinity. Okay, oops. So this is all these things that I've said before here. And if it would be nice if this was the whole story, but this is not the complete picture. There are many other possibilities for descent. And the basic idea, there's 2 points. When I had lots of, I can do descent with respect to any exact operator in the algebra. And I looked above and I asked which one, I only was interested in ones which actually were not in the isotropy group of the origin. So, and that's why we landed on P plus and P minus. But as soon as I do descent once, and now I have a light-like line, I actually have to ask which of those exact operators are not in the isotropy group of the line, not just the origin. So now there's more operators. In other words, they might leave the origin fixed, but they could bend that line in some way. Well, it actually turns out that for light-like lines, the fact a conformal transformation will preserve the fact that it's light-like. So all it can do is kind of rotate the direction of the light-like line. But there are operators that do that. The M plus Z and M plus Z bar operators would rotate the L minus line and so forth. So then I have more possibilities for descent. When I got to this step here, I could have acted with M minus, say, 3 or something like that, and maybe gotten a new line, a new surface operator. And then there's another possibility, which is I could do descent by P plus. P plus moves it, but what if I did a descent by the operator P plus, I don't know, twice, M plus 3. That's also an exact operator. It's a distinct exact operator. When I exponentiate, it's a distinct group. And I know P plus moves the origin, but what's the effect of adding in this M plus 3 guy? And of course, there was this arbitrary coefficient, let's call it alpha, in front of the M plus 3. What effect would this have? In other words, do I find, in fact, a whole one parameter family of L plus lines in this way? So you have to kind of figure out this whole sort of space of possible descents. And as you go down this sort of descent tree here, more and more operators move these the isotropy groups of the lines or surfaces or whatever that you're trying to do the descent on are smaller and smaller. So you have more available operators to move it. So the end result is, so there's many more possibilities and you have to try to figure them out. And the current status is a picture something like this. And the gray ... parts are ones that we have not completely finished sorting out. And for instance, and there are a lot of identifications that are made here. So if I do this P minus descent to L minus, I could do an M plus 3 descent, an M plus 4 descent, any linear combination of them, linear combinations of M plus 3 and M plus, or P minus with M minus 3 and M minus 4 and so forth and so on. And it turns out all those different choices of linear combinations are equivalent in T and in T-dagger chi cohomology to the ones, the descents with these operators here. So even though you can get distinct operators with action and sometimes with distinct world volumes, they are equivalent in T cohomology. And so the sort of the T inequivalent classes that you get under descent are shown here. And we know, so up to here, this is very solid. We know that there are actually 3 different surface operators. The one that I called S, but also S minus and S plus. S minus and S plus lie in certain cross sections of the light cone in 4 dimensions. And then there are 2 domain wall operators, which are they both lie on, they both have the same world volume, namely they fill out the whole, they're 3-dimensional, so they fill out the whole light cone, okay? But they're not necessarily the same operator. They could be, you know, in the hypermultiplet case, they have opposite chiralities, fermions. And then there's other stuff and other possible descents, and it gets to be quite a zoo. And I'm sorry that we're working hard on it, but we have not completely sorted out all the cohomology equivalences among the different things that you can get here. And of course, once you have them, you also have to ask about their convergence properties once you put them in correlation functions. Okay. So this is, you know, this general picture, this descent tree of extended operators corresponding to every operator in the vertex operator algebra. We generate a whole set of operators like this in T cohomology. So this is just what I was saying in words. And then I wanted to finish up, and I see my time is basically over, so I'm going to do this extremely quickly. I wanted to finish up by just—
Can I ask a question before you proceed?
Yeah.
So for every operator O in the vertex algebra, you can create this tree. Is it clear that different trees do not intersect? Meaning that the operator that I get, the surfaces and the lines are distinct from the construction.
Yeah. So there are certain charges like the L0 charge, the U1R charge, and so forth, which are actually, and I guess that Z charge, I call it, which are preserved under the descent procedure. And those are enough to also characterize, you know, in some sense, the different supermultiplets that the Schur operator belongs to. And so Schur operators which belong to different supermultiplets, and all their descendants will be distinct as to maybe there's a possibility of mixing among, if you have multiple supermultiplets of the same, with the same shortening conditions, with the same quantum numbers.
So there could be potential sort of mixing if there's degeneracy in the supermultiple, in the shortening condition.
Yeah. Okay. I kind of doubt it, but I don't know for sure. Looks like Michele has a question.
Yeah, go ahead. Thank you.
Hey, Philip. Yes, I take advantage of this moment to ask you a question on the thing that you have said a little bit above. You mentioned that these correlation functions are meromorphic in the ZIs.
Yeah.
And I was wondering if there is any interesting information encoded in the residues.
Well, what I'm going to do is take a pair of these operators and look at their operator product expansion.
Yes.
And look at the poles in their Laurent expansion. And that's like exact, I expect that's where, you know, the interesting information is going to be. It's kind of the structure of this operator algebra. And so I'm going to show you in an example right now for the simplest case that I can compute in, which is a free hypermultiplet. So you get a sense of what this structure looks like.
Yeah, very good, because that's the relation to the algebra of fusion of these objects, right? It should be encoded in this information.
Right.
Okay. So I'll let you go. Thank you, Philip.
So I want to do this very fast. So you put a free hypermultiplet, which has some scalars and spinors, and the scalars are these super primaries. Let's organize them. So they have an SU2R doublet, but they also are a doublet of an SU2 flavor symmetry. So that's what these capital A indices are. And the one with the highest weight in the SU2R is a Schur. So this is a case where the superconformal primary is also the Schur primary. It has in the VOA weight 1/2. And in there's another operator. This is actually, from the point of view of space-time, one of the components of the SU2R current, but it's the thing that plays the role of that operator T of Z that I was telling you about in the Schur multiplet. And that's just rho 1 del Z rho 1 contracted on the flavor indices. So let's look at, let's ignore the moment map for the moment and for this talk, and just talk about these guys, their descent lines and surfaces, and their OPEs. So let me first just start with the easy guy, this free scalar. So here's the Schur operator. I'll just call it rho A, and I'm just, in other words, dropping this index. And then you do the descent procedure. The L plus line is the integral of psi twiddle 1 dot A along x plus. The L minus is psi 1 A on x minus. And the surface operator, if you work out the algebra, is just the integral along x plus and x minus of the z derivative of rho 2 of the not the Schur guy here in the x plus x minus plane. And I put in some normalization factors for later convenience. And then we can take these guys and ask what their OPEs are. So x and y are any one of these four. And they all have this following form. And I'm just going to pick off the singular pieces. And in this case, the only singular piece is always proportional to the identity operator, okay? Doesn't matter whether it's line with surface, and so forth. And so they all have exactly this form with some real coefficient b here. And here are the real coefficients that you get. So rho with rho it's 1. That's the normalization of rho. Rho with s turns out to be -1. S with s is -2. The rhos with the l's, the rhos and s's, the bosonic guys with the fermionic guys, and give 0, which makes sense, of course, if that's what they close on. But you can have L pluses with L minuses closing like that. So you just have to do the calculations to see this. It's not too hard, but it's a little bit of a mess. This is a bit encouraging. First of all, it's a check of the meromorphic dependence that was argued for in general terms. But what you're really interested in is, let's put in this this VOA stress tensor operator and see what the OPEs are with this. And this is where you get your first inkling of what's going on. So here, with the 1/2, this rho 1 del z rho 1 operator is T. Then the L plus descendant of it is this particular the integral of this particular combination of operators, and similarly L minus of the kind of chiral conjugate of that. And S is this thing. It has a del Z rho 2, del Z rho 1 type things, and psi twiddle del Z psi type terms here. Okay. And these, and then it's considerably more work to start computing the OPEs of these guys. But let's take the OPEs of one of these T descent operators with any one of the row descent operators. Then they all have the following form, which looks a lot like what you would expect the T row OP or the T with a primary OPE to look like. It would look like you would say, oh, it's a conform, if a conformal weight, well, A1 over 2 would be a conformal weight times the row operator plus del Z over Z times the row operator. That would be the usual thing, saying row is primary with respect to T. But now something interesting happens. First of all, what are you have to compute these coefficients. They depend on X, Y. And depending on X and Y, what operator you get on the right-hand side can change. So, now I'm going to encode in this table these two real coefficients, A1 and A2, and which operator it is that appears here on the right-hand side. So this one here, this is the usual thing, saying row A is a primary with respect to T, primary operator with respect to T. Let's ask if S of row A is primary with respect to T. And the answer is already no. T acting on S of row does not close on S of row on the right-hand side. It closes on row on the right-hand side. And in particular, the L-1 mode of T, right? In the usual, in a vertex operator algebra, in the usual Virasoro algebra, that generates translations. That should be the del Z operator here. But here we're saying that that L-1 mode on S does not give me del Z of S. It gives me del Z of the local operator rho. So we're saying the OPE of a local operator with a surface operator closes on a local operator. This is what we find in, again, it's crucial that you do all of this in T cohomology. This already tells us that this is not, that this extension is no longer has the structure of a vertex operator algebra or of a conformal vertex algebra, because the L-1 mode of the Virasoro operator does not coincide with the derivative operator, the translation operator in the vertex algebra. So it's a more general object, a vertex algebra, not a vertex operator algebra. And similar things happen here. And as you see, we thought we had computed these, but we made a mistake. So we still have to figure out those coefficients. And then even more complicated things happen when you take the OPEs of the T's and their descendants. And I'll just write down some of the leading terms. First, the TT OPE is the usual Virasoro algebra. It gives you a C equals -1 VOA. You do, when it's kind of allowed by the quantum rules, you do get these guys closing on the identity with a 1 over Z to the 4th guy. And it turns out the ones that we computed all have the same coefficient. This one, unfortunately, the SS one, we're still working on. But they close on things which are not, so to speak, just built out of T's and its descendant operators. For instance, the T L plus or L minus OPE closes on a dimension that, both of these have H equal to 2. So in that kind of grading by dimension, this looks like a dimension 1 operator. And it's a normal ordered product of the local row operator with the L plus minus descendant line, L plus descendant line, descent line operator based on row. And in fact, they all have this. So this is a perfectly good new operator in cohomology. No.
Sorry, how much do you have your 15?
So this is basically the end.
Okay.
So I just wanted to show you these results to show you that, okay, whatever this extension that we're finding is, it's not as pretty as a VOA. It seems quite a bit more complicated, but yeah. And so there was an early question about whether there's some sort of categorical general construction of what this extension of the VOA is. And I don't know, already in the case of the free hypermultiplet, it's looking complicated. There's lots of patterns here, but I don't know.
Yeah, so I think this is the part that few of us are actually interested in seeing, but maybe since we're reasonably over, yeah. we can stop.
Let me just,
we can go to discussion session.
Yeah, right. So let me just conclude with a sentence, which is that, so we have this, there is this extension of the VOA. That's a property of 4D n equals 2 superconformal field theories. We have not shown, and it's not clear that it's an interesting extension, that it really contains, in some sense, new information beyond the VOA or not. And so that's still work in progress. Okay, thanks.
Okay, let's thank Philip. Really wonderful talk. Since we're over, maybe we can have one question, and we'll stop the recording and move on to discussion session, and whoever wants to hang out can hang out.
So Ronan asked a question in the chat. Is the H preserved by descent not the L0 eigenvalue? So I defined an L0 as a certain generator of the space-time superconformal algebra, and that eigenvalue H is preserved by descent. But that L0 is not the mode of the T operator that you might want to call L0. That's the thing that's breaking down. So it was nice to call it L0 when it turned out to actually be the modes for them when they formed a Virasoro algebra, but it's no longer true that the modes of, we should give them a different name, the modes of T form a Virasoro algebra, but those guys no longer coincide with the operators that I called L0, L1, and L-1, which were, the fact that they coincided in the VOA, in the original paper, was completely mysterious, right? There's no reason why the modes of this T operator, which didn't have anything, not that it didn't have anything, but it wasn't the stress energy tensor or a component of the stress energy tensor in space-time. Why they should coincide with the in their action on operators with those things that I called L0, L+1, and L-, which were components of the stress energy tensor in space-time. So, okay, maybe, I'm sorry, I probably said that in a very confusing way, but it's precisely that identification which is breaking down when you do this extension.
Let's thank Philip one more time for the really wonderful talk. So I'll turn off the recording and